I'm excited to tell you today about some recent experimental results building on the work of a lot of theory that have really excited me. They've taught me new things about what I imagine the future of quantum computing is going to look like and the way in which it reveals things about our universe that I think would be otherwise inaccessible. Thank you for joining me today on this interesting exploration, and I hope to be able to share some of my excitement with you in a way that gets you excited as well. And so, what am I going to talk about today? I'm going to talk a little bit about quantum machine learning and something we've been calling data advantage. So what is quantum machine learning? Besides kind of smashing buzzwords together, you might think that, it pertains to helping out neural networks or other kinds of applications, but I'm actually going to focus in and try to bring you to a point of view that really views quantum computers as processing data that comes from our physical world. And so I think an interesting way to look at this and what we would like to do with quantum machine learning is to take a point of view that looks at what it means to achieve, say, a quantum advantage on something. So we often talk about computationally limited problems. And what I mean by this is these are problems with simple inputs and sort of a known computational procedure, even if it's sort of hard to compute. And so examples of this are, say, factoring, where you're given some input and you know how to do the task that you would like. But in one case, we hope that perhaps it will take a very, very long time on a classical computer, maybe even exponential time. And a quantum computer is going to help us do that task in a much, much less time. So perhaps even if we're very lucky, we move something like an exponential to a linear time scaling algorithm. And for this type of problem, we're always going to have to deal with, say, the structure in a problem, advances in classical computation, and advances in sort of the power of our algorithms and our very good ability to build these great devices, such as classical supercomputers, microprocessors, etc. Another kind of problem we can look at, and this can go by many names, and what I'm going to call it today is sort of data-limited problems, are problems where they're limited by the lack of the availability of data. So the amount of measurements I can do on a physical system, or the number of, say, quantum states that I can transduce into my different device. And in this case, we're going to have a very different situation. So imagine that, for example, I'm getting states, and I'm going to be a little bit more precise about this later, from some data source that's external, and I'm going to collect in copies from, say, a quantum sensor or perhaps another part of my quantum computation. And in this case, when I have a limited number of these copies, my quantum computer might be able to process that data in a way that if I cut off the samples, there's simply no way for the competition to catch up. And this basically means that no matter how much compute I do on the classical side, I'll never be able to bridge that gap. And one reason we became interested in these problems is we started to learn of problems in an intermediate regime that I'll mention in a second, which are these problems we've started calling data-assisted problems. So these are problems like the top category that have some known computational procedure, but the complexity of that problem can fundamentally change if I give you a little bit of data to help you. And so one way to motivate this kind of data-assisted problem is to think about a situation where I'm given some quantum circuit and some inputs that I'm going to give to this quantum circuit. So say that it's just a vector of size p that I'm going to put in these amplitudes. And I'm imagining here that p is very, very small compared to the size of the space. Maybe it's order 1, maybe it's a few dozen. And my task will simply be to compute the output of some quantum circuit measuring some Hermitian observable, but I'm going to let that quantum circuit be as long as it wants to be. So this could sort of be an arbitrarily hard or interesting computation, and you realize that it's at least as hard as, say, factoring or BQP or any quantum task you'd like to do. And because I let it be incredibly long, it could perhaps even be more difficult than that. But instead of just giving you the problem, in this case, I'm going to give you a little bit of data. And so I give you some number of samples of this task for my inputs and my outputs. And I want to take a look again at the form of exactly what I'm predicting. So if I take this just expression here and expand out the input that I give it, and I kind of crunch the numbers a little bit, what I find out is that this form, basically, where I've rolled the complexity of all this very long quantum circuit into this simple, P by P matrix. And so what has really happened here is that by giving myself a little bit of data, I've realized that this is at most a quadratic function on the entries of this xi with only p squared coefficients. And so from learning theory, I sort of know that I need at most p squared of these things. And the bottom line is that for this very contrived problem, with no data, this was an arbitrarily hard quantum circuit. And with a little bit of data, this was an almost trivial learning task. So you might say, well, this is kind of a bad setup. You shouldn't have put this data into the amplitudes. This feels a little bit contrived. And you'd be right, but it's an interesting starting point to ask, if this problem can be assisted by data, what can we say about the more general situation? How can we start to understand when, for example, a quantum computer could be replaced by a data set? And so this started us on an exploration that we began a few years ago in this power of data in quantum machine learning. And we tried to formally separate these classes where data is available and can assist you in a problem for ones for which you fundamentally still need the quantum computer. And so you learn about this kind of general task, and you might start to wonder, well, when does this actually apply? Does this actually apply to some of the interesting problems people have been talking about for applications? And in some sense, it does. So the follow-up work by the same authors, Robert here, who you'll see his name appear many times as the first author, showed that for interesting problems like learning ground states, in some cases, you're able to prove that a few pieces of data are sufficient to make interesting predictions about ground state properties. And so as you read papers like this, you start to wonder, is the fate of quantum computers to provide training data for classical models? While that would be an eminently interesting and kind of practical application, it would fall a little bit short of our hopes and expectations for one of the most advanced technologies that humanity is working on right now. And so you say, okay, well, where do I most fundamentally need a quantum computer? And luckily, the same authors and others that you'll see as collaborators here, like Jordan Kotler, came up with some interesting ideas for how to imagine quantum computers interfacing really with the quantum parts of our world, where really you can't substitute that classical computation in the same way that you perhaps can in other places. And so today, I'm going to tell you a little bit about an experimental realization of some of these theory ideas, and indeed some new theory ideas that help us boil down to the essence of what a quantum computer can really do to help us show new facets of our physical world. And so to do that, I'm going to have a setup where I'm essentially going to imagine experiments where data comes in from a quantum sensor, and I'm going to come and have two different settings. One will be a quantum enhanced setting, and one will be sort of the conventional setting. In the quantum enhanced setting, the difference is essentially that when I receive quantum states, and these could be from other parts of my quantum device, these could be from sensors, I'm allowed to keep at least one or more copies of that state. So you imagine it producing many samples as some physical process. And I just keep one around in quantum memory, and I'm able to act on that and other copies at the same time. And the conventional actor will be as what we think of as measurements today, where I get some quantum state, and then perhaps I immediately perform some measurement down to classical data before receiving another sample. And essentially, we're going to imagine these two setups that we've depicted here as this quantum state coming in and being able to be stored in a quantum memory by this quantum actor or learner here. And only towards the end do we collect classical data and then do that processing. Whereas on the bottom case, we're going to imagine each time a sample is received, we can do an arbitrary quantum manipulation to it, but we must measure and fix our results after that manipulation. And these will be the only essential differences between the two settings. And we're going to imagine this in the case of processes as well, which you might imagine as an even closer to physical reality setup, in which I create some probe state, I move it close to the environment I'm interested in, allow some process or that system to act on it, receive my probe state back, and then do some kind of measurement on it. Where the distinction between the two is still similar to before, where the only difference here is I'm allowed to carry some state forward in memory. And essentially, the bottom line of this work is, if you don't remember anything else, is that you achieve an exponential data advantage with only two copies on two different tasks and efficient compute. And more or less, I'm going to elaborate on what those tasks are, just how simple we were able to make them, and recall that this is a data advantage in these cases. So it's a case where if the the number of samples or the thing that you're measuring is cut off, there's essentially no way for any amount of classical compute to compete with you. So in order to better understand these, we wanted, as a big task in this work, to boil it down to the simplest objective that we can have an advantage on. And so what we're going to do is imagine that we're given, we have some source of a state row that's going to keep providing us that state. And we're going to make that state sort of as simple as possible. So it will be a mixed state, if you're not familiar with this notation, of just kind of the identity mixed with some amount of a long poly operator. And so if you're less familiar with this kind of state, just know that the essential setup of the problem is that the form of the state is known to all parties trying to identify the state. But what we're trying to determine is the identity of this constant alpha and this state P, or rather a learning task that sort of requires implicit knowledge of it. So an important thing to note is the state is actually unentangled, but is not factorizable, a property you can have in mixed states, but not in pure ones, and interestingly can be realized in a depth 1 Clifford circuit. So you're going to see a lot of Clifford circuits in here, and you might be tempted to think these things are classically simulatable, but an important assumption here will be that we don't know the identity of the state, and actually the processing will still require quantum manipulations. So we cannot actually simulate this process in the sense that we still need to receive quantum data. So we're going to compare two setups here. So these are the states that you're going to be given, the conventional setup and the quantum enhanced setup. Each one will produce some amount of classical data that will be given to a learning algorithm, and we're going to predict some property. And so that task is we can take any amount of measurements you want, subject to the constraint of the setup on n copies. You collect a classical data signature of that state, and then you are given some new poly operator O, and you're asked to predict this value. So this is after you've received all the states, collected all your data source is now cut off. I give you a new operator, O, which can be any of, this 4 to the n possible poly operators, and you tell me that value. Or alternatively, I could give you 2 challenge operators, and you tell me which one is greater. And so I think it's important to emphasize, say, before you see the quantum circuits, which are able to perform this task, kind of where the challenge and sort of meat of this was. And I think it's largely contained in the fact that we wanted to make these tasks as simple as possible, both for the experiment and to help with the understanding of where some amount of quantum advantage comes from. And this task is showing that essentially no possible conventional experiment can do better than what we propose. And so the result summary is that basically if you're receiving each of these copies, and you can do arbitrary computing to each copy, but must measure, so the conventional measurement scenario, you're going to need an exponential number of copies to do better than some accuracy with some probability. And essentially, the sketch of the proof is kind of a nice follow-on to some proof strategies that were proposed by some of the collaborators in previous work, where you can prove essentially that for this form of a state and the reduction to a discrimination task, you can see what the optimal POVM is, and there's simply no way to do better than this. And so this is an information theoretic limitation that can't be overcome by additional computation. This is kind of the meat of what has to be shown for the tasks as you make them simpler and simpler, that it's still incredibly challenging or near impossible with limited number of samples to do better with any classical strategy. And so then you say, okay, well, what's the quantum strategy? And in fact, it's incredibly simple for this particular task. So remember that we're given these states row, even though we know how to prepare them here. The setup is that we'll be blinded to their preparation. We'll know their form, but not the details of what's inside them. And then essentially, we're just going to take these very standard Bell measurements, and we're going to talk more about how general those are later. And I'm going to collect 2n classical bit strings. So I'm going to take exactly 2 copies, measure across those 2 copies, and get these bits out. And essentially, the summary of it is that this is going to require a number of samples that's more or less independent of the number of qubits and a very efficient computation time. And I'll tell you quickly that there's a very easy way to show get the exact quantity that you want out, but our focus will actually be on the ability to learn that without having to know the right answer. So to kind of summarize the scales of separation between these two tasks, recall that I'm giving you n copies of this state row. You're allowed to take any measurement you want on the n copies. You collect a classical signature, and now I predict some new value to an error that you tell me. And essentially, between these two scenarios, if I'm stuck with arbitrary processing on one copy at a time, I have to take an exponential number of these samples. So if the data source just becomes cut off at some point, it could perhaps become impossible to do the task. Whereas in the other setting, I need an extremely small number of copies. Essentially, it naturally reveals itself to me. So I mentioned before that we kind of don't want to have to know the answer ahead of time. If you imagine going out into the wild and collecting quantum data from your universe, you don't want to have to know the answer that you're looking for. And this is indeed a hope, say, in machine learning as well, where we see some pattern and we would like to just be able to learn this pattern overall. So what I mentioned before is this technique collects 2n classical bits. So we can kind of think of this as a Bell sketch or some kind of feature of my state. And we ask, can this feature be used to learn things about the state that I'm interested in? And this is important too, because if you put it on a real device and an adversary can learn things about the noise, perhaps you could do better than the theory would predict to do an imperfect implementation. And actually, we're going to compare two settings here where we do a supervised learning setting, and we show that even training on smaller sizes allows you to generalize to large ones without having to implant any structure by hand. And to me, a more striking demonstration will be that, in fact, these features are so good that they learn very well in an unsupervised setting. And we'll say more about that in a minute. And I think it's interesting to put this kind of work into a larger framework and imagine how we're going to emulate and process data in the future using a quantum computer. So you can imagine, what are the sources of my quantum data? Something like another quantum computation on a different system, perhaps an analog simulation, or even an advanced quantum sensor using multi-qubit data to collect the information you want. And all of these are going to have to perform a step where they move the data into a computational medium. And so we often call this step transduction, of moving between one medium of data and another into this sort of quantum buffer. And as far as we know at the moment, quantum computation is going to require some form of error correction. And so we put this into a quantum memory that can be long-lived and protected with all of our guaranteed techniques. But this stuff over here, if you kind of look at it, this might always essentially be unprotected. So I'm gathering information with some imperfect sensor. And without knowledge of special symmetries of that system, it's not clear how to arbitrarily reduce errors in that step. Whereas in the second part, it is. And so essentially, once it's protected, we do some kind of data processing and extract the information. But if this part's always unprotected, it becomes very interesting to ask, how does this perform in real conditions? And so proofs have some flexibility, but it's not unlimited. And this suggests a real part where you can bring in a quantum device and start to say, well, I can now emulate this on a real quantum device at system sizes where this kind of processing would be difficult. And in fact, I can blind myself to the state preparation, but I can imagine that doing that state preparation still has an amount of noise that can emulate the noise in transduction. And essentially, we're going to set this up on our Google Sycamore chip, which we run entirely through the cloud. And essentially, we'll have some set of memory qubits and some set of system qubits that we're going to lay out, which are just these separate copies of the state. And so how does our experimental demonstration work? We imagine giving ourselves n copies of this state row, and we're going to train on noiseless data at small sizes to ensure that that structure is essentially learnable from the data in a way that generalizes to large sizes. And what we find that when we train this, the quantum prediction accuracy does quite well, and the classical one is essentially bounded at some information theoretic limit. And the summary of this, and keep in mind, this is all data from the actual device, is that as you grow the system size, the number of experiments required to reach a certain accuracy on this task starts to show a huge separation between quantum and classical. So here we have a rigorous lower bound on the best possible classical strategy, is that dotted line. And we have some actual classical strategies that are executing to show you the separation between a typical one and that lower bound. And the quantum performance, even on a noisy device, shows often 4 orders of magnitude or more separation, even at 20 qubits per copy. So reminder, that's 40 physical qubits. And we're able to show this massive data advantage, which, recall, cannot be overcome by any amount of classical compute. And so we've learned about states so far, and you might have argued that those preparation circuits that we used didn't really push the limits of our device. So reminder, it was just that depth 1 Clifford circuit followed by measurements. And so we wanted to learn about an even more interesting physical scenario. So reminder that we're able to do this process learning as well, where now I'm going to prepare some probe state, expose it to a process, do measurements, and get those states back. And the task will be instead now given access to some process in times, determine if it's a random time reversal symmetric, so kind of all real entry matrix, or just a random unitary. And the circuit will look eerily familiar, except now it will sort of be two-sided, where I have some Bell preparation. I expose it to this unknown process, and I do a measurement. And once again, I get out 2n bit strings as some kind of feature. And so the layout on this one is a little more intricate because what we're going to do is actually 1D and 2D randomizing dynamics. And we'd want to go with kind of as long in depth as we can. And essentially, that's going to mean that for 1D dynamics on 40 qubits, we have hundreds or close to 1,000 gates. And for these 2D dynamics, we're going to do almost 1,400 gates hidden in this process that is unknown. And so it's quite a challenging experiment and kind of an interesting demonstration of the robustness of these features for learning. And so the part of this that kind of excited me the most, as I mentioned before, is that in fact, once we collect these Bell features, we're interested in cases where I can discover an unknown phenomenon. So something I'm not specifically looking for. And a good setting for this is actually unsupervised machine learning. So if we think about taking these 2n features, we average them and take their variance, and we get a feature vector for each one of these processes that I'm given back and plug it into one of the simplest sort of unsupervised learning methods that we can think of. So we give them some squared exponential kernel as a similarity measure, plug it into just kernel PCA, and let's find out what happens. So I just handed you a bunch of processes. I didn't tell you what you might find in them. And if you look at them in the conventional scenario and you kind of look at their kernel PCA, you'd look at them and say, well, if there's something in here, I can't tell the difference. It's probably just the same process. But I go to this data collected on just 2 quantum copies, so these generic Bell measurements that you've seen over and over again, and they basically perfectly separate without me having to do anything. And so this is exciting for me because it means that if I had collected this data from the wild, knowing nothing about the task, I would say, okay, there's definitely 2 distinct physical processes here, and now I can go study these further, but this is something that would have been totally invisible to me without this quantum device. And so we can say a little bit more about the quantitative separations between the two, but essentially the quantum enhanced experiments do much, much better than the conventional, as you might guess. And I'll just say a final thing about how we expect to collect kind of this noisy data in the future. So I mentioned how we always imagine getting this corrupted quantum data in. It gives me some mixed state out. So one model that you can have for this is that there's just some amount of uncorrupted data if your error is quite low, and some amount of orthogonal errors. So it's not always a perfect model, but in some cases it's a nice one, as other papers have explored. And you might recall this technique, which has been used now a little bit in the NISQ era, sometimes called derangement or virtual distillation, that lets you sample from higher powers of the density matrix. And if you go look at the circuit there, it's once again these 2n bits that come from Bell measurements. And so a final result we had in our paper was to kind of connect ideas like this. So if you have one destructive swap test that gives you virtual distillation, you can use swap as a generator and get something like quantum PCA. And what we proved is that essentially with multiple copies, this is an efficient process. And with only single copies at a time, there's an exponential overhead. So quantum computers are allowing us to refine data from interesting quantum states in a way that's essentially provably impossible without multiple copies of this state at a time, at least when the data source is limited. So what's the summary outtake here? Is my punchline for the day is if we could find a suitable data source, and that if is in bold for a reason, this is a big question of where we should find multi-qubit quantum data, then our cloud quantum devices today allow us to learn things that would otherwise be inaccessible. And recall of this difference between quantum, computational, and data advantage, that there's no supercomputer computation that can come and compete with what has been done here. And so this work, we proved advantages in state learning, process learning, and quantum PCA, and did an experimental demonstration using Google's device over the cloud, learning up to 40 physical qubits and 1,300 gates. And our hope for this work is it inspires additional work on quantum data sources and sensors looking beyond quadratic advantages. We hope to find deeper connections to physics and interferometry, go beyond Bell measurements, and ask if these proof techniques can tell us something about existing learning tasks. And with that, I'd just like to acknowledge the people who did the hard work in all of this. Of course, Robert Huang led many of the proofs and other technical work here, Michael that made it possible to interface with the cloud, and Brooks for his late nights fixing up the experiment. And of course, all of our collaborators here, some of whom are speaking today, like Jordan Kotler on the theory foundations for this work, and the whole quantum AI team, because bringing up this chip to make these experiments possible is incredibly hard and requires detailed work and expertise from a lot of people on the team. It would have been possible to name all of them by name. And of course, finally, I'd like to thank all of you for listening. Thank you.